Let's take a look at another example where we're asked to compute the integral from 0 to 2 of the fraction 1 over square root 16 plus 4x squared. And because there's not an x next to the dx, the simple substitution u equals 16 plus 4x squared just won't work for us. So we're going to need to use the trig substitution. And our goal is for 16 plus 4x squared to become 16 plus 16 tangent squared. You have to change of theta. And you have to change the constant from 4 to 16 because we need to have the same constant if 16 plus 16 tangent. That way the 16 factors out and we're left with 1 plus tangent squared, which is secant squared of theta. Now in doing this, we need to find out what our dx is. So I'll solve for x in the first equality. And we don't need to worry about the square root of a square being the absolute value because we're actually letting x equal 2 tangent of theta, which gives us everything above it. So if x is equal to 2 tangent of theta, then my dx would be the derivative 2 secant squared of theta d theta. Now, as for the bounds of integration, just like any other substitution, if we change our variable, we have to change our bounds to match it. These bounds are x values. X is 0 to x is 2. So I will change those. If x is equal to 2, then 2 tangent of theta must equal 2. That gets me that tangent of theta is 1. And that gives me that theta must be pi over 4. Remember that we are within the bounds of theta being between negative pi over 2 and positive pi over 2. And that's the only answer between those bounds. X is equal to 0, so 2 tangent is 0. If tangent is 0, the only solution is theta is 0. So now let's put all of these back together. So we've got the original integral, which I'll rewrite down here, with its new bounds. So instead of x is equal to 0, I'll write theta is equal to 0. I can just write 0. Instead of x is equal to 2, theta is pi over 4. And now we're going to replace the 16 plus 4x squared with 16 secant squared. And the dx from the original problem is replaced with 2 secant squared theta d theta. Now, I'll need to simplify a bit. So on the bottom, I have the square root of 16 is 4. The square root of secant squared is absolute value of secant. And here the absolute value does matter because this is not our choice to let x is equal to 2 tangent of theta like we did before. Here we have the square root of a square, which is the definition of absolute value. Now fortunately, looking at our bounds, and this actually does not rely on the fact that we're dealing with a definite integral. Remember, our promise when we do these sorts of substitutions is that theta is between negative pi over 2 and positive pi over 2. In fact, in this problem it's between 0 and pi over 4. In either case, the cosine, and therefore the sine function, is always positive on that interval. Between negative pi over 2 and positive pi over 2, the x value of the unit circle is positive. Therefore, the absolute value signs can be scratched out or erased. So that's good news. The absolute value, and this often happens, can just be canceled away because we know that secant has to be positive, and then we can get rid of one of the squares, by dividing the secant by the secant. So where does that leave us? Well, I've got a 2 over a 4, so I guess I can cancel those, leaving me with just a 2. And the resulting integral is from 0 to pi over 4. I've got 1/2 secant of theta d theta. Now to integrate this, we just need to use the formula for the integral of secant, and that formula is 1/2, excuse me, it's just the natural log, absolute value, secant plus tangent. Now, suppose for a moment we wanted to turn this back into the original variables. Now we don't, because of the fact that we changed our bounds from 0 to pi over 4. But if we wanted to, we could. This would be the same thing as 1/2 natural log secant of theta. How do we figure out what secant of theta is? Well, just take a look up here. I could take this first equality and solve for secant in terms of x. I get that secant squared of theta is 16 plus 4x squared divided by 16. And then I could take the square root and get that secant of theta is the square root of 1 plus 1/4 x squared. So it's not the nicest looking thing in the world, but it works. Square root 1 plus 1/4 x squared. Tangent, of course, being much simpler, from up here at the substitution step, tangent is just x divided by 2. So I can make that replacement as well. And that would be my general antiderivative, plus c. Now the issue is that it's not a general antiderivative. I have bounds in this particular problem. So I did a little bit more work than I even needed to. So I'll get rid of this, because that would be the answer for an indefinite integral. For the definite integral, since I changed my bounds, it's even simpler. I'm just evaluating from 0 to pi over 4. So now I'll plug in the top minus the bottom. 1/2 natural log secant of pi over 4 plus tangent of pi over 4 minus natural log secant of 0 plus tangent of 0. Let's do some simplifying of the trig involved here. Secant of pi over 4 is the square root of 2. That's root 2 over 2 inverse. Tangent of pi over 4 is 1. Secant of 0 is 1. Tangent of 0 is 0. Notice that the natural log of 1 plus 0 is 0, so all that goes away. So my final answer here, 1/2 natural log square root of 2 plus 1, and you can drop off those absolute values because the square root of 2 plus 1 is positive. And that will not simplify any further, unfortunately, so that is my final answer.